Hi everyone. This is just a brief introduction to waves, different types of waves, and wave characteristics. This is the start of a new unit. Hope everybody is doing okay. This would be obviously a lot more interesting in class because we could get out some demos, but I'm going to try to find some videos that demonstrate what I'm talking about. So we'll start by defining a wave as a traveling disturbance. A key thing to know is that in a wave there's two types of motion, and I'll show a video of this in a minute. The one type of motion would be called the vibration or the oscillation. This is the back and forth motion that we are familiar with from the unit we just finished. This would be describing the movement of individual particles in a medium, and it's generally around some equilibrium position due to some restoring force, that when it's pulled from its equilibrium position, there's some restoring force pulling it back. Generally, this is not constant speed, as you guys know from an oscillation. The individual particles in almost a sinusoidal way do not travel at constant speed. It's constantly changing speed. Propagation is what we call the movement of the disturbance throughout space from one point to another. The key is it's the movement of the disturbance itself and not the movement of the medium. The matter does not propagate. It's the disturbance itself that travels. Sometimes waves are often described as an energy transfer mechanism, and that's just because they transfer energy without transferring the matter. Throwing a ball across the room is not a wave. That's an actual propagation of a mass through space. This is a really good, just quick video to kind of show what's going on here. And what you're seeing there is movement back and forth of the medium as the person, kind of does that right here. And then the thing that actually travels is the wave itself. But notice here that the medium is traveling back and forth this way, and that the medium is the thing moving, but that the wave travels across the table. And this little element of spring here is not traveling across the table. Really important. Important to note that it was the wave itself that traveled across the table at constant speed, and the vibration of the oscillation was back and forth. Now, we're going to hear a lot of words about waves. There's several different ways to classify waves. So the first one that I'll highlight here is mechanical versus non-mechanical. This course concerns itself exclusively with mechanical waves. Mechanical waves require a medium, things that we would have like a wave traveling on a spring or through a string. Certainly sound is a mechanical wave, and the medium for sound is air, although sound travels through all sorts of media. Sound can travel through solids, sound can travel through water or liquids. This course is exclusively focused on mechanical waves, things with a medium. Non-mechanical waves are things that travel without a medium. And I guess the question that begs is then what is it that's vibrating? And generally we would say that it is the field that vibrates. So if it's an electromagnetic wave, it'd be a magnetic, the electromagnetic field is the thing that's vibrating. But we really see non-mechanical waves in the context of light and electromagnetic radiation, but these are things that do not require a medium. We don't handle this at all in this course. It's exclusively a topic in AP Physics 2, and so that would be a way to see some of those topics. Transverse and longitudinal is really about the direction between the propagation and the oscillation. So I'll show a video of this, but in transverse waves, the direction of oscillation is perpendicular. Trans, opposite, transverse, perpendicular to the propagation. Sometimes people think of waves as transverse waves, like when they first picture a wave. However, longitudinal waves are just as legitimate, and in this case, the direction of the oscillation is parallel to the propagation. Really important, you can create both of these on a spring wave. And sound wave is definitely a longitudinal wave. Let me show you what that means. A longitudinal wave has the oscillation in the same direction as the propagation. You can see this, the matter itself is oscillating this way and the propagation is in the same direction. A transverse wave is oscillating this way, and in a perpendicular direction, the wave itself is traveling. Just a picture to remind you, just screenshots of what we just saw. So transverse and longitudinal, two different waves to classify. Pulse versus continuous. Continuous or periodic waves have a frequency, and I'll show an example of this, whereas pulse waves have only one pulse. There's certain characteristics, and we'll get to this in a minute, that you cannot measure on a pulse wave. This is a great time to introduce you to FET's wave on a string. If you can kind of see the head or the title up here. If you want to just kind of Google FET wave on a string, you should get this. This is what comes up in the default. Sometimes to introduce this, I make certain changes immediately. One of these that I do is I say no end. That way it's not reflecting yet. I'll show you other stuff as we talk more about waves. I usually move the tension to kind of medium, and I completely remove damping. And you guys know that damping means there's going to be some loss of amplitude as this thing goes. So normal tends to be okay. It's a little fast. If you want to slow it down, then do so. This will also change the speed a little bit. So this is the pulse function, and you can set what's the amplitude of the pulse and the pulse width. But when you click this green button here, you're going to send a pulse. Now, it kind of goes out to pasture here, and if you want, you can pause it. But the point here is that only one thing is sent, and that there's not another one coming. That's called a pulse wave. A continuous wave, when I get this started, is going to be produced by a continuous oscillation. So this actually has a frequency, and we'll just kind of get that started. It is the transverse continuous wave that people think of most when they think about waves. Now, if we pause this, we kind of see the what's produced here is like a sine or cosine wave. There is some difference, though. When we saw a cosine or sine wave before, it was the position of this oscillator versus time. This is a screenshot. This is a pause screenshot, and the two axes here, or the two dimensions, would be the y and the x. So that's a little different. They're both the same shape. So the actual position versus time of this thing and the screenshot of this look exactly the same from a shape standpoint. But this is this would be a periodic, and it's obvious why it's called periodic, because it has a period. This thing oscillates back and forth, and contrast that to a pulse wave in which there is only one. Just a couple of videos, or sorry, screenshots to show that idea there. Now, there's a couple parts of a wave. And there's a couple of things you'll only see on a continuous or periodic wave. So just showing these two words. This is a crest. Crest is kind of the high point. This would be the equilibrium position, and this is a trough, T-R-O-U-G-H. This is important because we're going to show some characteristics of waves. So wave characteristics, there are 5 of them that we'll talk about all the time. They are amplitude. Amplitude is the size of the wave. You guys know it kind of as the maximum displacement for the equilibrium position. This is actually a function or a characteristic of either transverse or longitudinal waves. There's the speed. This is the wave. This is the speed of the wave itself, the disturbance, not the individual particles. There's the frequency, and this is only a characteristic in a periodic or continuous wave. There's no such thing as a frequency if there isn't a second oscillation coming. Period and frequency are very related. And then finally, there's the wavelength, and the wavelength is the distance between crests or troughs. And just to show you an example of that, this is a screenshot of the continuous wave there. This would be the amplitude. The amplitude could also be measured from the equilibrium position to a trough, and the wavelength would be the distance between crests in this case, or could also be measured from trough to trough. just want to show you how you might measure some of these things. If you want, you could slow it down. It gets a little bit fast. But this has some, I'm going to get the continuous wave going here. This has some kind of rulers and a timer on there, and just kind of how you would measure these things. Okay. First of all, you know that you know how to measure amplitude. So what we could do here is just wait for one of these to come by, kind of pause this and show that in fact the amplitude of this, or the total displacement from the equilibrium position, is about 0.75 is what's set, and you can kind of see that's right in that range there. So that's kind of it. We could have also measured that, I can't turn it around, but you could measure this from there to there, which would be equilibrium to trough. And that's about the same distance. To measure the wavelength, you could just set your ruler at one position and then measure the new wavelength. Notice we didn't set wavelength, and that's over the next couple days. That's something that's going to emerge as something that's determined by two different factors. So this wavelength appears to be about 2.5 centimeters. Now notice I just got amplitude and wavelength from a screenshot of the wave. In order to get the other three, I would actually need something that depends on time. So to get the other three, I would almost need to kind of take this time. If I wanted to get the speed, for example, I could watch this crest move. So if I kind of started the timer and then let it go, and then maybe I could wait until it had traveled, I don't know, 5 centimeters, and then I could see this is the time. So this crest went from 0 to 5 centimeters in this time, and then traveling at constant velocity, I could just divide that distance by that time. So 5 centimeters divided by 1.32 seconds would give me the speed of the thing in centimeters per second. Okay. Now I could also measure period or frequency. Period would be the time between cycles. So I could just kind of set a line here, right? I could reset this, and I could say, let's start here. And I'm waiting for the next crest to come along. So pause when, I don't know, about there. And it looks like then the period is about 0.66 seconds. It took 0.66 seconds for one crest to come by. And I could just keep going here, and, there's another one. There's another one. And it looks like in 2 seconds, 3 crests came by. And so I could divide that 2 seconds by the 3 crests to get the same time per crest. Some of you might also notice, though, that this is also the oscillating frequency of the source itself. So if I waited till the source kind of was at a crest and then started here, I could play and watch this go down, go up. That's 1 cycle. That's 2 cycles. And then here's a completion of 3 cycles, and what do you know? It's right around 2 seconds. So whether you get the period watching this go up and down or watching this come by, it's going to be the same period. And the final classification of waves is actually a traveling versus a standing wave. I'll show you this in another applet in a minute, but here's the basic definition: is traveling waves appear to move. They appear to propagate, whereas standing waves appear not to propagate. Standing waves just appear to go back and forth in one place, and you'll recognize examples of this. But it's important also to know that that's actually a misnomer. In reality, standing waves are a specific pattern of interference. Sorry, that's misspelled. That should be interference. That is made up of several traveling waves. And let me show you what I mean. This is a standing wave simulation done by Walter Fent. If you just say standing wave simulation on Google, it should come up. I've unchecked some things just because we're going to talk about standing waves. I just kind of wanted to show you what this looks like here. So this is before there's any reflection here. This is actually what a traveling wave looks like. You can kind of see it. It appears to be propagating, just like you guys would expect it to from the applet that I was using with a wave on the string applet. So what ends up happening here in a minute, however, is that there's a reflection, and the reflection kind of starts coming back here, and then it starts interfering with itself. And standing waves are a specific pattern of interference. And so right now it looks like it's moving, and these ones continue to be coming in and moving. But as it interferes with itself, all of a sudden these kind of different crests and troughs build. These are signaling different positions called nodes and antinodes, and that's what that's indicating. And we will study standing waves. It's a huge item. But when the interference pattern is complete, what you get here is a situation where it looks like it's no longer traveling. These crests and troughs appear to be just going back and forth as opposed to towards this. I'm not going to go way into standing waves right now because we are definitely going to learn a lot more about them. So hope this was helpful, and I'll see you in the discussion for any questions about the homework, or if there's any questions about the lecture I'll open that up for Wednesday's class and you can put those there. Thanks.